Dear students, welcome to the online class. I am Dr. SSC Hiremat. In this video, you are going to study about the Debye-Huckel's theory of strong electrolytes, about its assumptions. The following are the assumptions of the Debye-Huckel's theory of strong electrolytes. First one, all strong electrolytes are completely ionized in all dilute solutions. All strong electrolytes are completely ionized in all dilute solutions. Means degree of dissociation of that is alpha equal to 1, or that is 100% ionized. They are 100% ionized. Then second assumption, the ratio of equivalent conductance at concentration C, that is lambda C, and equivalent conductance at infinite dilution that is lambda infinity, that is lambda C divided by lambda infinity gives only the ratio of equivalent conductances. It does not give any information about degree of ionization. It means in the case of weak electrolyte, this ratio gives the degree of ionization, whereas in the case of strong electrolytes, it does not give any information. It is just a ratio of the rate equilibrium and that is equivalent conductances. Then third one, the equivalent conductance of strong electrolytes increases with dilution, and it is due to the increase in ionic mobility. Means in the case of weak electrolytes, the degree of dissociation increases and the equivalent conductance increases with dilution, whereas in the case of strong electrolytes, the degree of dissociation is 1 means almost completely dissociated, but still there is increase in the conductance, and it is due to the increase in mobility of the ions. Fourth one, the two ions present in the solution obey the Coulomb's rule of Coulomb's rule. That is, there is a force of attraction between oppositely charged ions and is equal to that is F equal to Q1 Q2 divided by D into R square, where Q1 Q2 are the charges on the ions and R is the distance between them and T is dielectric constant. Then fifth assumption, each ion is surrounded by oppositely charged ions and then solvent molecules attach to them. Thus a positive ion is surrounded by many negatively charged ions and a negative ion is surrounded by many positively charged ions. So the ionic atmosphere is formed. Ionic atmosphere is formed. It may be represented as suppose this is a positive ion and there is a negative ion. The potential of an ion that is represented by psi is the work done to bring an ion from infinite to that point. That is, psi is equal to integration of f into dr. This is integration of q1 q2 dr divided by d into r square. That is, psi is equal to q1 q2 divided by d into r. Suppose this is equation 1. In this theory, we are going to derive the expression for activity coefficient of an ion of a strong electrolyte in solution. That is, F or F plus or minus. Suppose psi is the potential of a cation and Z plus is the valency and E is the charge on one electron, then energy of one cation is given by Z plus E into psi. Similarly, energy of one anion is given by Z minus E into psi. Suppose this is equation 2 and this is equation 3, and here not and, it is comma. At appreciable distance, the potential psi is taken as 0. Then n plus 0 is the total number of positive ions and n minus 0 is the total number of negative ions in the ionic atmosphere of appreciable distance. If n plus and n minus are the number of positive ions and negative ions respectively in a small region, then according to Maxwell's distribution, we get n plus equal to n plus naught into e raised to minus z plus e psi. Suppose this is equation 3, and n minus equal to n minus 0, then e raised to minus z minus e psi. Suppose this is equation 4. This is about the number of positive ions and negative ions present in a particular portion of the ionic atmosphere. Then charge density in the region is the difference between the total charge of positive ions and total charge of negative ions. that is charge density. Suppose charge density is represented as rho. Charge density rho. Therefore, rho is equal to number of positive ions n plus charge on the positive ions z plus and charge of one electron is z, that is E, minus charge on negative ions, total number of negative ions and valency of the negative ion and charge of the electrons. This is equal to, we may take the value of n plus and n minus from this, that is z plus E into bracket n plus naught e raised to minus z plus E psi minus z minus E n minus 0, then e raised to minus z minus E psi. Suppose this is equation 5. For univalent salt, z plus equal to z minus equal to 1. For univalent salt, z plus is equal to z minus is equal to 1. For an ionic atmosphere, of appreciable distance, total number of positive ions that is n plus 0 is equal to the total number of negative ions which may be taken as equal to n naught. Then equation 5 becomes here rho is equal to z plus z minus gets cancelled and E is taken as common, and this n plus 0 and n minus 0 is taken as equal to n0, then e raised to minus z plus E psi divided by kt minus e raised to minus z minus E psi divided by kt. When z plus E psi is very small, then e raised to minus z plus E psi may be kt may be taken as equal to minus z E psi z plus divided by kt. Similarly, e raised to minus z minus e psi divided by kt is taken as equal to minus z minus e psi divided by kt. Then equation, suppose this is equation 6, equation 6 becomes, then equation 6 becomes rho is equal to n naught e as it is, and this is taken, first term is taken as equal to z plus minus z plus e psi divided by kt, and minus of this is minus but charge is minus, and this also becomes minus z minus e psi divided by kt, which is equal to n naught, and e raised to, you take this e also, that becomes e square. Then z plus z minus may be taken as equal to 1, and that is e square psi, and this is equal to 2 divided by kt, that is rho is equal to 2 n naught e square psi divided by kt. Suppose this is equation 7, which is the expression for the charge density. As we know, charge density is the total charge on the positive ions minus total charge on the negative ions, that is equal to rho. If z plus and z minus are not unity, then the number of ions may be expressed as is expressed in terms of ionic strength for a unit volume. That is, n naught may be taken as equal to 1 by 2 summation of n I z I square, where n is the number of moles of ions and z I cation or anion, it is equal to 0. Actually, the ionic strength is expressed in this way, n naught equal to this. Then equation 7 becomes rho equal to 2 n naught e square psi divided by kt. This n naught may be expressed in 1 by 2 summation of n I z I square. Then this 2 get cancelled, and you are going to get e square psi divided by kt into summation of n I z I square. So this is equation 8. For an ionic atmosphere, of radius r and a charge density rho from Poisson's equation. Rho and psi are related by equation 1 divided by r square dou by dou r of r square and dou by dou r of psi is equal to 4 pi rho divided by d, that too with minus sign, negative sign. This is with negative sign. This is also with negative sign. Suppose this is equation 9. By substituting the rho in the equation 9, we get 1 divided by r square dou by dou r of r square and dou psi divided by dou r is equal to 4, that to minus 4 pi divided by d, and rho equal to e square psi divided by kt and summation of ni zi square. Suppose this is equation 10. By substituting minus 4 pi epsilon square divided by d k t summation of ni zi square is equal to k square, we get 1 divided by r square dou by dou r of r square dou psi divided by dou r is equal to minus, not minus, it is k square psi is equal to, now let us take it as equation 11 and this is equal to 12. Equation 11 gives the expression for kappa. This is kappa. Now physical significance of kappa. Physical significance of kappa. The reciprocal of kappa that is 1 divided by kappa gives the radius of ionic atmosphere. Radius of ionic atmosphere. Its value depends upon concentration of electrolyte. For 1 molar solution of univalent electrolyte 1 divided by kappa is 3.1 degree angstrom.